field of human endeavor has seen greater innovation or faster development than integrated circuit technology. Each new development accelerates our ability to innovate, and each new breakthrough leads to further breakthroughs. The frontiers of the possible continue to be pushed back as theories become realities at an ever-accelerating pace. As our ability to build circuits with greater complexity and higher speed continues to advance, the future seems limitless. But there is one thing standing in the way: our ability to test what we can now create. VLSI devices, which are designed and developed using high-speed computers, have had to be tested using a much slower and increasingly unwieldy instrument-based approach. And as IC technology becomes more sophisticated, this shared resource approach becomes even more complicated and costly. This testing bottleneck has become the major problem in new circuit production, slowing productivity and hampering research and development. Some VLSI devices are being delayed up to a year in getting to market. The traditional approach of sharing limited testing resources among a much larger number of pins clearly cannot continue. We cannot create tomorrow's integrated circuits using yesterday's testing technology. What is needed is not a more complicated instrument, but an entirely new approach, an approach that recognizes that a tester is above all a real-time computer system, not just a collection of instruments. An approach that provides complete tester resources to each pin simultaneously. Traditionally, this solution has been considered too expensive, requiring a technical capability that was years away, until now. This is the MegaOne, the first tester that is not an extension of the shared resource approach, but the first and only system with a true tester per pin architecture. An architecture that will redefine the way people think about testing. With complete and independent tester resources behind every pin, the MegaOne has the hardware capabilities to test what could never be tested before. Its simple architecture gives it a testing accuracy which is unmatched. Simplicity translates into a cleaner software model that allows programs to be developed more efficiently. The elegance of the tester per pin approach has long been appreciated, but it appeared to be much too expensive and would require technical innovation that was beyond current capabilities. The story of this technological breakthrough is really the story of a breakthrough in creativity, the story of how teamwork and commitment were able to turn an elegant idea into a practical reality. This is the story of the development of the MegaOne. In 1975, Howard Marshall, a test system designer for Hewlett-Packard, and Steve Bisset, a circuit designer for Intel, recognized the growing problem in testing and saw the potential for solution through a new approach.
It was obvious at that time that the development of microprocessors was accelerating at such a pace that the automatic test equipment that was available was very rapidly going to run out of steam.
We could foresee that as microprocessor volume grew, then the prices would fall dramatically. One of the obstacles toward price reduction was relatively high test cost, and we proposed a test solution that was an order of magnitude cheaper than the available test systems of that time, the Q8000 test system.
Smaller, faster, and less expensive than its competitors, the Q8000 soon became the standard in its field. In less than 4 years, the Q8000 had tested more microprocessors and more non-volatile memories than anyone in the business. The Q2 family of test systems extended the capabilities of a Q8000 and brought production cost effectiveness into the engineering lab. With more than 1,000 systems in operation throughout the world, Megatest had earned a reputation for the most reliable testing products on the market. But the testing industry as 1979. In just a few years, chip complexity had grown from 20,000 devices on a chip to over 200,000, with no end in sight. It was the age of VLSI, and testing could no longer keep up. It was time for a radically new approach.
We wanted to develop a revolutionary architecture that would satisfy the needs of the ATE user for the next 20 years, and that would serve as a basis for developing a whole series of systems that had a common architectural base, a common design philosophy, but that used new technologies and new components as they came along to improve performance and improve cost effectiveness as the years went by.
Steve Bisset recognized that to accomplish his dream, they would have to design and build the tester as a real-time computer from the ground up. Not a collection of instruments, but a single architectural entity. This task would require the talents of a very special person. Steve turned to his old friend, Dr. Richard Swan, professor of computer science at Carnegie Mellon University and developer of the famous CM Star, one of the first multi-processor computer systems.
I had some background in computer architecture which hadn't been previously applied in tester design. So I came in thinking that this was an area with where some new ideas could make a difference. I thought I would have the resources and some really good people to work with.
At the beginning of 1980, Dr. Richard Swan assumed leadership of a new product team. He was joined by Mike Catalano and Bob Miller, two key people in the design of Megatest's Q2 test system.
Difference in delays of the different paths going into the MUX?
Yeah, as a matter of fact, it looks like
The big departure that we could make, that we looked at very closely, was the whole issue of a tester per pin, in particular a timing generator per pin, which initially looked prohibitively expensive, but clearly had enormous advantages.
We'd had this hunch that this tester per pin approach to doing it was elegant, it was exciting, it offered repeatability, and it had a future to it. But there were some serious questions that had never been answered.
What was being considered was not a modification of a shared resource testing system, but a whole new approach. Megatest was trying to rewrite the book on ATE design. But was it possible? Were there a sufficient number of unknowns to ruin their chances for success? And could they accomplish a project of this magnitude in a reasonable period of time? In the early months of 1980, the project team conducted experiments and collected data in search of the answer. In July, at the product review team meeting, after much analysis, argument, and consideration, the decision was made.
Have any chance of becoming widely accepted outside of the university world?
We came out with a decision at that point that we would do everything we could to provide as much computer power within an economic spectrum as we could, and we chose to take the risk on per pin timing, and the whole company backed that. I think that was a sort of a unique thing about Megatest, that at that meeting we got a consensus of most of the leaders at Megatest, and we haven't looked back.
With the goal now set, the team began work on each of the major subsystems: the computer, the software, and the tester mainframe itself. But if tester per pin architecture was to be feasible, the first critical task of the mainframe group would be to find a way to make a timing generator at a greatly reduced cost.
The beauty of this is if you get this little piece here to work, if you get that timing generator to work with a bit of data behind it, you just make more of them.
Well, that was a mouthful, too, because this is probably conceptually and in terms of performance one of the most difficult items in this entire system to build.
In 2 years, the timing generator was complete and ready for fabrication. The Megatest process of group effort and review resulted in an elegant and cost-effective design. In August of 1980, Megatest made another important and at the time risky decision to adopt the Unix operating system as the basis for their software.
Back in 1980, it didn't have the visibility that it has now, where it's a cover article in electronics every other month. But at the time, it was the only non-proprietary operating system of any significance at all. And we saw it as the best operating system available. So we decided to adopt it. And it looks like the rest of the world has followed with us.
But no computer available could run Unix and at the same time handle the huge data requirements and real-time demands of per-pin testing. They would have to build their own.
So we came up with a multi-processor architecture where we could actually devote a CPU to a process that required real-time attention and also run the time-sharing load.
We needed a lot of computer power, and in particular, a lot of physical address space in order to directly access the 48 megabytes in the tester itself. There was no commercially available system. We possibly could have adapted a VAX to do it, but it would have been standing on our head, and it would have locked us into a relatively unsatisfactory situation.
Extensive computer power was also used in the design of the product itself. In 1980, Megatest developed a sophisticated CAD/CAM system for designing and auto-routing 10-layer ECL boards, a system that would shorten the turnaround time of these boards from 8 months to just 3 weeks. As this early CAD design work progressed, the tester per pin architecture began to take shape, igniting new ideas for further simplification.
We had the whole system partitioned into boards, and it set out to actually go and do the detailed design of each board. And then it was another board that it turned out was not feasible, that we had packed too much stuff on it, and we had to shift some things around. And in the course of that, someone realized, you know, a different way of doing it, which, you know, is just unbelievably elegant and reduced the number of board types and basically made the whole system a lot simpler.
You know, such a constant evolution that in fact I left for vacation for 2 weeks and came back and found out my whole memory system had been repartitioned.
We have a team effort, team atmosphere that allows us to critique each other's work in a non-political environment. It's a classic team effort.
As a result of that, you had a lot of people helping you with your work, and you would help other people, and the problems were shared. So I think what you do is you end up with a situation with effectively having a larger design team because you're working more efficiently.
The software team, under the direction of Rob Mullis, had been making rapid progress as well. The decision to go with Unix had turned out to be even more beneficial than first thought. It was quickly becoming the most popular multi-user operating system and offered programmers unprecedented simplicity in the control of their tester.
Available to us in Unix, very easy ways to write filters so that we could have simple translations into...
The tester per pin architecture allows us, for the first time, to be able to provide the user with a transparent machine. The test engineer no longer has to worry about buses and things. The test engineer simply has to think about the part, think about the type of test he wants to happen on the part, what kind of edges go where, what to look for, and the test engineer can express that in the terms the test engineer understands, not in terms of the tester, but in terms of the part.
In September of 1982, the first board design, the timing generator, was completed and sent out for fabrication. By December, 5 more boards were complete. As the system began to take shape, the pace quickened.
Things were pretty fast-paced, and people were working very hard at that point.
All you can do is sort of sit there and keep grinding away, and basically you sort of forget about sleep.
Very late nights, people were working very hard. There was a lot of camaraderie at about that time.
1983 would be a good year for the Megatest team. 3/4 of the system boards were completed by March, and by the end of April, the 3 boards at the heart of the MegaOne tester, the timing generator, the vector memory, and the pin electronics boards were ready to be debugged.
And those 3, which are the 3 high-volume boards in the system, are a slice through the tester. If you have those, you basically have a tester.
We had bet a large part of the company's future in 1980 on a completely new architecture And the architecture was dependent on elements that had never been done before.
On May 18th, 1983, after only 3 weeks of debugging, these elements, the first pin slice, were ready to be integrated for the first time. It was a crucial test for the MegaOne project. Success here would validate what were only theories until now.
That's right, we have the load set.
Yeah, the load set.
Okay.
Okay, how about drive highs, drive lows?
What would you like? -2 volts?
Okay, 2 volts.
What kind of frequency should we go for?
40 megahertz.
Yeah. Sounds good.
Okay.
Okay. Are you on pin 0 or pin 1?
Pin 1.
Okay.
Okay, fine. All right, let's the state of...
At first, there was nothing. Tense moments passed as no signals were seen.
Okay, not getting them yet. Not getting them yet.
And then, success.
All right, look at that. Hey, Rich, come over here.
A single square wave indicated the birth of a powerful new tester. The hard work had paid off.
Right.
Suddenly, it just signals appeared at the output. Everybody started jumping around, and people came from all over the building. They paged it, and I guess it was the first peak in what had been a very, very long, hard period of development. Here's your tester. Hey, great.
That was a really exciting time because we went from just pieces of paper and some components to something we could show, something that was actually there.
What do the edges look like?
The edges look okay for a prototype.
When we got that pin slice together and made it all work, there's no longer any doubt in anybody's mind. And if the crank had been turning, it started racing at that point in time.
In just 3 years, through a combination of hard work, innovation, and teamwork, Megatest had designed and built the most powerful test system in the world. The first system with full testing resources behind every pin. The same computer power Megatest successfully brought to the design of the tester also served to streamline the manufacturing process.
We have an MRP system that manages all resource requirements for manufacturing. It orders all the components. It schedules the delivery of those components. It schedules the building of boards and systems. A recent thing that we've introduced for MegaOne is semi-automatic assembly with a laser-guided system.
These machines have their database driven directly off our CAD database. Initial results have shown stuff error rates that would be considered incredible by normal industry standards.
We can semi-automatically assemble a board like our pin electronics board that has a couple of thousand components, where previously it took us 2 or 3 days of technician time to stuff such a board. We can do it in 6 or 8 hours.
This planning and efficiency not only applied to manufacturing, but to customer service as well. In fact, many of the aspects of training and service were designed into the MegaOne from the very start.
Over 20% of the hardware in the system is devoted to diagnostics and to serviceability of the system. We can read both ends of every cable. We can identify the board IDs of every board in the system electronically. We can even do such things as tell when a fan filter is dirty by monitoring the rotational speeds of the fans in the system. Beyond that, we've really tried to take again the advantage of the system, or take advantage of the computer in the system, to be able to offer online tutorials that will let a new user explore different aspects in the system in an interactive manner.
Simple, powerful, elegant. A tool as sophisticated as the devices it tests. A test system that is designed to free the creativity of its users.
The basic advantage of this system to the end user is productivity.
Test development times may be shortened by as much as an order of magnitude.
It will be used by most people in the course of developing the next generation of chips, and I think it may actually help further the technology there.
We have an environment where just because it's big and successful, it hasn't taken the thrill of driving it forwards out of the people who do this work.
Forget the past. Let's figure out what the problem is. Let's use all today's technology, both hardware and software technology, and focus it really on solving the VLSI tester problem.
With the introduction of the MegaOne, the testing bottleneck has been broken. The major problem restricting the development and production of VLSI devices has been solved, not out of solitary insight, but out of the combined creativity of people working together. This has been the story of where this breakthrough came from. But where it came from is not nearly as important as where it will lead.